about factorization homology of rigid braided categories.
Right. Well, I'm really happy to be you all's company this week. I look forward to some stimulating conversations. Um, Thank you for this invitation to share my work. So here's the main result that I'll talk about. I put it up on the board, and I might try to be strategic and leave it up there for most of the time. We'll see how that goes. Um, what I thought I'd do is state the main result uh, and some features that this has. State some key calculations, which are themselves theorems. State some corollaries of this result. And then depending on time, I'll explain how to implement this construction. So, and I'm just going to give a disclaimer that um, I'm totally bought into infinity category theory as a binary category theory. And essentially everything I say has that in its backdrop. I'm not going to emphasize those elements too much, though I'm happy to respond to questions about that if you'd like. So there's an infinity here, and if that's not something that is in your wheelhouse, I encourage you to just remove infinity and just see one before. Okay, so this result is joint with John Francis. And everything I say today is joint with John Francis. It's uh, there's some background, and it's very related to work with Aaron Maselji and Nick Rosenblum. Um, and for that matter, I learned a lot about just linear category theory through writing a book with these two, um, though that's not going to be present today so much. So the main result says, so pick a dimension, and I invite you to just substitute that dimension to be 3, because that's where the most awesome applications are anyway. So pick a dimension and pick a commutative ring, at least for this phrasing. The statement of the main result is each rigid braided monoidal category is linear over K. Let's call it R. It determines an assignment. It assigns to, let's say, a framed 3-manifold. By framed, I mean it's the data of a trivialization of its tangent bundle or a parallelization. It assigns to it a chain complex. And the zeroth homology of that chain complex is something that is of a special interest. I'll come back to that later. But outputting a chain complex is advantageous in a way that this crowd appreciates. One can also input not a 3-manifold, but a surface. And that surface need not be framed, because that would restrict it in the connected compact case to a torus, right? But it's equipped with an injection into a trivial rank 3 bundle. And every orientable surface admits such, or every surface does. So that's the main result, is a construction. Let me now talk about
But,
features. Yeah, please.
is there any relation between these two layers? Say if the surface doesn't perform this will have.
There's definitely relation. I think of this case like so this data, given this data, I think of a surface as an extremely degenerate 3-manifold. And there is a relationship between them that that'll come up in just a second. It'll be on a board hidden by that one. Not just a second, but just a few minutes.
Literally just the same data as take the 3-manifold to be the surface across the interval. Like, why did you say extremely degenerate? It could just be a finite interval.
Oh, so that works too in the case that the surface is orientable. Yeah, so that's totally good too. I guess I'll do it this way. So here's some features of this assignment. So one is that its values on Euclidean spaces are rather explicit. So the value on R2, which is a surface, is chains on the moduli space of objects. So obj there to me is the set of objects and isomorphisms among them, forming a groupoid, and it's the chains on that groupoid. the value on R3 is endomorphisms of the unit. And these are not just definitions, these are computations. So these are like lemmas. Some other features that this assignment has, and this one maybe looks innocuous, but it's like the greatest outcome of this construction, in my opinion. There's an action of the entire topological group of frame diffeomorphisms on this. So just contrast this with other assignments that input a manifold and output like a vector space. You might be familiar with a lot of such, and they go by choosing a triangulation of the manifold and then doing something from there. And in doing so, there's just not going to be an action of the entire group of diffeomorphisms, right? Only diffeomorphisms that preserve that triangulation, or you might try to bootstrap that up, if with a lot of work, up to an action of the mapping class group, zeroth homology, or something like that. But this is much stronger. It's an
That's continuous.
What's that?
That's continuous.
In that sense. This is what I mean by continuous.
Collection of chains or something.
But yeah, it's just logical, right?
What's that?
It looks like it's a chains on the group. Like,
Yeah.
in this sense, just in the DG sense.
Yeah. So this is a chain complex, and this is a topological group. So chains on it is a DG algebra.
We have a statement about mapping class groups like.
And then on zeroth
homology.
for free, then it descends as an action of the mapping class group on the zeroth homology of this chain complex.
Only zeros.
Huh?
Only zeros.
Well, this is much stronger. So so this gives a map from diff tensor R, right? An action map like this. Yeah. In particular, mapping class group on the zero homology. Yeah. So to have this action kind of reveals a sense in which no choice of triangulation is needed to implement this construction. It's functorial in two senses, and these two senses, merging them together, results in some pretty interesting functoriality that I'll talk about in a little bit. So one sense in which it's functorial is if you're given a framed open embedding between two 3 manifolds, such as a thickened circle embedding into R3, so that's a framed link, then that determines a map between these chain complexes. Another sense in which it's functorial is given a proper fiber bundle going this way, that determines a map in the opposite direction like this. And an example of a proper fiber bundle is simply the projection like that. So just the fact that it's functorial in these two ways means we get a map from, so given a framed link in R3, you get a map from R2, from the factorization, from this value on R2 to this value on R3, which are the two values that are known. Back to that in a little bit. Here are some other features of this.
In the R3, sorry, real quick. In the R3 example, that's a chain complex just in like degree 0 or?
Oh, so, right. So when I said that R is a braided monoidal infinity category over K, I have in mind that R is enriched in chain complexes.
Okay.
So this is inherently a chain complex. And in examples, see when this is rep QG, then this is actually just in degree 0.
And so is this morphism between
There's some other features of it.
can I ask a question?
Yes.
is this map between these chain complexes up to homotopy?
Nope. Nope.
So just honest map of chain complexes.
Oh, do you mean, is it a map of chain so, right.
In what category is it a morphism?
Yeah,
Is it homotopy category?
Thank you. So this is part of what I had in mind by embracing the infinity. So I'm working in the infinity category of chain complexes, which is it's stronger than the homotopy category of chain complexes. But it's weaker than the ordinary category of chain complexes. Does that answer that question?
Yeah. Okay, thanks.
Thanks for that question. Yeah.
Your blackboard. So is it from R1 cross S1 to R3? Or is it?
R2 cross S1. So that's a 3 manifold.
You want to embed the 3 manifold in R3?
Into R3, yeah.
The neighborhood of another.
Yeah, so it's like it's just an embedding of S1 and then normally thickened a little bit.
Okay,
Yeah. These are great questions. Keep them coming. So another feature of this assignment is that it satisfies a Fubini type result. You're given a framed surface and a framed curve, so just oriented curve, then the value on that product is if you know this, it's the alpha version of factorization homology of a braided mineral category on a surface studied by David Jordan and others in this room. And the output of that is a category. And then you can apply the beta factorization homology, which is essentially the Hochschild homology, the case where C is just a circle to that. So this is the left-hand side is the new thing being discussed in this talk. The right-hand side is a concatenation of previous constructions. And lastly, this assignment satisfies a local to global result. It's excisive. So here's a schematic in dimension 2. If you're given a partition of the manifold as 2 manifolds glued along a common boundary, then its value on that glued thing is quasi-isomorphic to the value on just the left thing and the right thing along this middle thing. And indeed, there's a sense in which this is a category object. That's a right module for it, and that's a left module for it, thereby making sense of this. So this is a Cohen construction. We saw in Christoph's, much like we saw in Christoph's talk.
Can I ask a question about that?
What's that?
Can I ask you a question about
Yeah,
that?
please.
So you have a framed 3 manifold,
Uh-huh.
right? And you want to decompose it over a surface.
Yep.
It seems that the framing on the 3 manifolds, what it induces on a surface is not a framed surface.
Yeah, great. Actually,
So like for instance, can you always find a Haggard splitting that is compatible with this excision, or is there an obstruction?
great question. So this was even a note that I had in mind to mention exactly like with you in mind. So no compatibility of the framing is in this statement. No compatibility of the framing is required on sigma or on the boundary. Now, if we want to recognize this as, which I think you have in mind, as actually the alpha factorization homology of this, in order to write, these are okay notations. In order to write this, then yes, we have to have the framing of the 3 manifold splits along that boundary thing. But if I'm willing to entertain just an abstract category object, I can rightfully call this, we don't need to do that. So, but if the framing does not split along the boundary, then this cannot be described any other than a certain beta factorization homology.
Just I'm having trouble like type checking this equation. So I know what the alpha thing is and I know why that's a category.
Yeah.
But you already told me a specific surface and you told me its value and it was not a category. So I'm like,
Right, yeah, thank you. So this is code for, so evaluate on this surface that I'm calling partial and now cross it with essentially the interval. Now that's a three manifold with boundary. And by concatenating the interval with itself, this naturally forms a category object.
But,
Much-
but the framing will, the framing will get composed, no?
It's so the framing on this is not the product framing of a framing on partial and a framing on that. It's the inherited framing from a little interval in there. Yeah.
and then you just want me to like raise the sort of C bullet comma K in that formula over there, like.
C bullet this.
Yeah, you just wanted me to write down space of objects instead? Is that what's sort of
Um,
you're doing in the under the hood in this category?
So in the case where this maybe happens to be R2, right? Then this will be simply R itself. Yeah, so if that happens to be R2, then this is just the category, will turn out to just be the category, the phenomenal category R itself. Yeah. Thanks for these questions. So I'll emphasize in summary again, the left-hand side is a global value, and the right-hand side, this is an explicit expression for achieving that global value in terms of lesser values. And so any splitting, such as any old dart splitting, will be applied here, but unless it's essentially a lens space, then this will be more complicated than the good old alpha factorization homology of the braided monodal category. And then as a last remark, as I hope to get to, informally, what this value is a moduli space of R-labeled framed graphs in M. And it's essentially a derived version of spring S. And just to appreciate the sense in which it's derived, if you're familiar with spring nuts, and there's a great survey by Christoph for this that I learned this from. Instead of modding out by isotopy moves, keep track of that as kind of an isotopy determines essentially like a one cycle, et cetera, et cetera. Though this construction is not built in that way exactly, but that's the way of thinking about it. Okay.
And so, sorry, could you please repeat what are these alpha and beta in the Fubini statement?
What are the what in the Fubini
Alpha
statement?
and beta in red.
Yeah, thanks. I should have mentioned this. Okay, if you look on this slide, so the name for this chain complex, I will call the factorization homology. And that's a term that some might know already. There's papers written about this. And to emphasize that it's a, like, it's not the first version, but it's an upgraded version. It's the beta version, not the alpha version, but the beta version. So it's just beta it's just an optional little term to remind us that it's, if you happen to know what factorization homology already is, it's not that. It's a new version. And so in this formula Fubini, what's being emphasized is that, so there's a beta, that's the left-hand side is the new version. And this alpha is to say that if you know what the factorization homology was previously, it's that version, so the original. And in this formula, the most interesting case, just where that's a circle. And in that case, I'm going to erase this and just say it's the Hochschild complex of that. This,
So the old version gives you a different output. It gives you a category, yes, rather than.
yeah, exactly. Yeah. And this is the Hochschild complex of that category.
Ah. And is this specific to dimensions 2 and 1, or is it for any for any dimensions?
There's a sense in which it's true for any two dimensions, but I can't write Hochschild complex in that case.
Ah. And it's also true for bundles rather than direct products?
I don't know of how to phrase that exactly, but I'll bet that there is some kind of statement.
Well, I mean, if you integrate over fibers first.
Well, yeah, I can imagine. So for both of these, the way I think there is a statement like that in terms of push forwards of factorization homology. But I haven't taken the care to think about what that statement would be exactly. And it would be like integration along the fibers kind of thing.
Mm-hmm. Thanks.
Okay, well, thanks for these questions. Let's see if this works. Is this too low? Good. Okay, so what are some computations of this assignment? There's some easy ones to mention immediately. So here's an example, and it's a theorem that this is true. So we could take A to be an E3 algebra. And given that, one can form its D loop. The type of thing that is in particular a braided monoidal category. This is a braided monoidal category.
Sorry, what would be your favorite choice for the algebra?
Well, actually, there was one I was going to mention. So we could take it to be chains on the threefold loop space of a pointed space. I was going to mention that one in a second anyway. So there's an example. Were you looking for something else, maybe? Yeah. Okay. I mean, this is a pretty good source of examples, but it's a very limited source of examples. But then deformations of them are very interesting, especially if X has a shifted symplectic structure, then that gives a program for how to deform this into a very interesting.
Is it known that we have this one?
Is it known what?
If just you have the shift spec structure, do you get the E3 algebra? Is it known fact?
Well, so but by AKSZ, then this has a differently shifted symplectic structure. And then I'm going to point to more experts in the room about BB quantization stuff. So perturbative Chern-Simons can be thought of as an example in this case. Yeah, so pick an E3 algebra such as this. Then this is a braided monoidal category, and for trivial reasons, it's rigid. Oh, did I mention rigid? Yeah, good.
It's just modules, right? It's a module, so.
No, this is this is like there's a single object, and then there's the E3 algebra worth of
Without completion.
so no like Karubi completion of this or anything like that.
Your
Very simple.
categories are flagged, or really I should ask, does your main result apply to flagged infinity one?
It does, yeah. So this is something that one can input, and in this case, this value over a 3 manifold of this So I'll emphasize this is the beta version, right? This agrees because this agrees with the alpha version for just A. But if you happen to already know what the alpha version is, this strictly generalizes that. And this is not definitional, this is a computation. So this is a lemma or theorem, and it's not easy. I'm not sure how to feel about that, if that's a good thing or a bad thing, but it's true. Another example is, and this is related to,
Can I ask a question? If you have a braided monoidal category, then if you look at the ext of the identity object with itself, this is an E3 algebra. So if I apply this construction to it, do you recover this category?
almost certainly not. Oh, well, almost certainly not.
So what do you get? So you for one braided monoidal category, you get another one.
Maybe relation.
Oh yeah, well, it's just the full subcategory generated by the unit.
Ah, okay.
Yeah. Which is a monodal subcategory, as you know. So another example is for A to be an E3 algebra, you can look at perf A. So these are like perfect E2 A modules. And there's a picture to go along with it, so like I'll label this by A, that by a vector space. So a perfect E2 module is a chain complex you could label by the dot with this kind of action. They organize into a braided monodal category, and here's a computation. Provided M is compact, out boundary, then there's this Morita invariance result. So this is Morita invariance. I say it that way because in the one-dimensional case, if M is a circle, then the left-hand side turns out to be the Hochschild complex of perf A, and the right-hand side is the Hochschild complex of A. Those are equivalent. That's it is. So that's the Pascal Morita invariance of Hochschild homology, and this is an upgrade of that to 3 dimensions.
The path A is more or less an independent completion of BA or something like that.
Yeah, yep, it's the Krubik. Yeah, exactly. So that's an expected result.
Is it the beta integral on the left-hand side?
Yeah, if I don't put beta, that's what this talk is about, so it's implicit.
Ah, okay.
Yeah.
But perf A and BA are not the same.
Right, yeah, this was mentioned in the room here, but perf A is the Krubik, is the infinity categorical setting, the Krubik completion of BA.
Ah.
Yeah, so that's why this is maybe to be expected. And it's only true if M is compact. Now, apologies for covering some of the board, I guess. So here's another example. Oh, actually, oh yeah. So another example is in the case where A is chains on a threefold loop space, a B chains threefold loop space of X beta over M. This agrees with chains on the space of compactly supported maps from M into X. And there's a similar similar statement that's just a little more involved to, oh, and this is provided if X is two connected. So if X is like BG for a simply connected G, then this is true. But if X is BG for a connected G, this statement as written is not true. However, there is a braided monodal category one can cook out of X, recover chains on the compact supported mapping space if X is only one connected. So I'm just gonna, it's just a little more complicated of a statement. So I'm just gonna say similar for X one connected or simply connected. So what the statement exactly. So there's, again, a braided monodal category to input into factorization homology, the output of which is chains on the space of compactly supported maps. Yeah.
So this example of triple loop loops, it looks like a monoidal center of something.
Yeah.
Or like not mono, two monoidal. So
I mean, it looks like the center of omega 2x.
Right.
Yeah.
Right. So can it be like made more general? So if you start with a center of if center of something, then
Yeah. Yeah. There's a statement that I might guess. It's like a Stokes's theorem kind of thing. But I know that it fails in some examples, and I know it's true in some examples. So I'm not sure what the correct statement is exactly, but that would be really interesting to figure out. Yeah. Before moving on, I'll just comment that if an E3 algebra is not familiar to you, an example of an E3 algebra, you could just take this to be a commutative algebra. In fact, you could just take it to be a commutative group, and then take its group ring associated to it. In that case, then in light of this result, this recovers the good old homology of your manifold with coefficients in that commutative group. So I bring that up to justify that maybe the term homology here, because all of these invariants are generalizing homology. In other words, there is a braided monodal category you can input to recover the good old homology of a manifold. Now, the key example, greatest interest for us, is so one can take the input to be rep finite dimensional Q, so that's generics, of say SL2C. Take it to be any quasi-triangular Hopf algebra. But in this case, then I know that this is, so this has a braided monodal structure. Grinfeld, I think 40 years ago. I think Christoph, you mentioned 30 years.
it's sort of in infinity part, right? If it's
Yeah, exactly. So this is in fact a braided monodal 1-1 category, I would say. Yeah, and that's an example of an infinity 1 category. Yeah.
So if you take like roots of unity, will be more interesting.
That would possibly be more interesting, but one would lose rigidity, and yeah, I would like to learn more to know how to fold in. I mean, rigidity is absolutely essential for this to work, and
Why would you lose rigidity at root of unity?
oh well,
You could take perfect, they can.
well, yeah, sure. Well, for the statement I'm about to write, I don't know how it's true at a root of unity. So maybe it's just some of you, in which case, please speak up. So let me write the statement. So first off, I have an item 1, but there's only one item. So the zeroth homology of this value on a 3 manifold, this case is isomorphic with the skein module of that 3 manifold. And so in particular, H0, in light of the Euclidean values I mentioned, is rational functions, and also there's an excision result for skein modules of stuff. And this is consistent with work of Cook. So it was to be expected in that sense. So this identification is really an observation on a certain way of presenting skein modules that is in some work of Turaev's that I wasn't aware of until I saw David Pobble and Sam Gunningham's work. Gunningham
I'm sorry to be that guy, but
Sure.
for many people, the skein module is something you get for an oriented 3 manifold. And use the fact that this category is actually ribbon in
Yeah.
a functional way. And I'm mentioning that because I really think it's complicated to extend what you're doing to the ribbon case.
Yeah, I
I
was.
agree you can define something like a skein module for a frame manifold. I don't know that this definition has appeared somewhere, but you can. It definitely makes sense. This probably, and it's very likely that this will be isomorphic to the one that people know, but it's not entirely obvious, I think.
Yeah, well, so the a couple so I was going to make a comment in just a little bit. So I'm working with framed manifolds here. Now, every orientable 3 manifold admits a framing. And what is kind of surprising is that many of these values of factorization homology don't depend on the framing any more than the orientation. I don't know that to be true, but I expect it to be true. And so this is consistent.
There's a choice of a ribbon structure gives you any time you choose a ribbon structure, that will give you isomorphisms between those.
Yeah, right. Yeah.
And the Hayek homology exists only on negative degrees or positive degrees here, or
So in this case, because there's no X in here, then this will be a positively concentrated chain complex.
so it's in just H0. There is no other homology.
Oh, I see what you're saying. There is higher homology. Now, whether or not it's formal, maybe that's the question you're asking.
No, I'm asking whether it exists only in positive degrees or maybe only in negative degrees. HI. Does HI vanish for positive degrees or for negative degrees here?
Oh, for in this case, HI vanishes in negative degrees. But not necessarily in positive degrees.
But in positive degrees, so there is a construction in this paper of that you mentioned that you take some Higard splitting, let's say, and you take some D modules attached to, or modules over the algebra of functions on space of connections, and then you tensor two such modules. So is it like derived tensor product? But then it would be in negative degrees, there would be non-zero contributions.
Maybe, are you working on the cohomological grading?
Okay, well, it doesn't matter. But is it the same thing? Is it like higher, like derived tensor products or derived homes for these D modules?
Yep.
Or for these modules of this algebra? Okay.
Conjecturally, those should be the same because we conjectured a formula for the derived skein module, but we didn't have a definition of the derived skein module. So I think David is proposing an actual definition, which then one would need to prove coincides with the formula that we wrote.
So you had the definition, David and co-authors had the definition, but it wasn't clear that it's independent on the Higard splitting or something like this. And now with this, it will be clear that it's independent.
Which is a thing to check.
Well, this thing about this tangent, like gluing and choosing framings on the surface and stuff, I wouldn't know how to. That would be a serious undertaking.
Yeah, agreed. I'll say a comment about this. I think the ribbon structure and the choice of framing stuff in just a little bit. I think we'll get there. I'd like to mention a consequence of the I erased it, of the functorial. I should have put that one. A consequence of the functoriality in this case. So if you're given a framed knot, given A in R3, a framed knot, and that determines a map or a zigzag of maps like this. But here's the frame knot K. Here's projection. And we discussed how factorization homology is oppositely functorial for maps like this, functorial for maps like that. So one achieves from this, from R2, R3. And I said what the Euclidean values are. This is chains on endomorphisms. So this is just endomorphisms. Good. This is chains on the objects. So one gets, let's call this JK, this map. So in particular, for every object V in R, one achieves a V of K there. And this recovers the Jones polynomial. The color Jones polynomial for V to be the fundamental representation.
Like monodromy with
What's that?
this J. Is it like monodromy with the object?
With monodromy, kind of with the identity. Yeah, exactly. Yep. So anyway, so I wanted to illustrate how these peculiar functorialities of factorization homology just manifestly produce the Jones polynomial in this case. Skip a couple things.
So,
So I,
so this result about H0 above, does it give you any hope of giving a new proof of finite dimensionality of this module?
yeah, I don't think so. I don't think so.
Mhm.
Yeah, I talked to Sam about just anything. Yeah, I guess I don't think so, and that seems to be confirmed by Sam Gunningham.
Mhm.
If you look at knots in S3 rather than R3,
Yeah.
then there's at least a potential that you would have like new derived contributions to the corresponding notion of Jones polynomial.
True, yeah.
Is that thing, yeah, is there anything to that?
Right. I don't know. I don't know. Yeah, so for, this is, I think, what part of what you're pointing out is not only given a knot in here, but there's like the moduli space of knots, the space embeddings of a circle into whatever R3 or S3. That determines a map from the space, the chains on the space of embeddings. That's for this. And I don't know what that produces. There's some corollaries of this. And logically, they do follow as corollaries of this assignment with the features that I've mentioned. But actually, both of what I'm going to say are statements that we prove first in order to prove the main result. So the logic of the construction of this actually uses these results independently. So, but I'll state them as corollary. Is the one-dimensional, that's the tangle hypothesis. Of one-dimensional tangles in ambient dimensions, and then certain singular versions. And I'll just write the statement. I don't intend to belabor it too much. So HOM between n-1 monoidal infinity 1 categories from a Bordism category of framed one-dimensional tangles in Rn-1 cross intervals into anything else. So that's just a rigid, that's why I used X. So we've been using R. So this is equivalent with the moduli space of objects of R. So that's a statement of the tangle hypothesis for one-dimensional tangles in ambient dimensional space. I'm not stating the singular versions, but certain singular versions also follow as a corollary of this. And so again, this is, if n is 3, this is a braided monodal category of just, it's the tangle category. The different tangles. Corollary 2 is there's an action of the orthogonal group on the category of En-1 monoidal rigid infinity 1 categories. And I'm going to put a K here to say K linear ones. I guess this is the first time that I'm keeping with the spirit of this workshop. Finally, here's something that looks like the space of tensor categories. And the statement is that there's an action of the orthogonal group on that. Now, so I'm encouraging us to think n is equal to 3. So the collection of braided monodal categories, rigid braided monodal categories, might be something some of you are familiar with. And such an action might be something you're not surprised by seeing asserted in light of the cobordism hypothesis. Let me just draw some distinction between maybe what you have in mind in this statement. So this action is like on this category. It's not on a Morita version of this category. So the action is by automorphisms, not by Morita equivalences. If that lands with you. And this is just a infinity one category. It's not some kind of higher category. And as a separate statement, thanks to David for pointing this out after John and I posted a paper a few years ago. And so one can look at, in the case where n is equal to 3, E2 algebras. I'll just put alg2 that are rigid. So this is in cat, comma 1 over C. So this is braided ordinary categories. And this action just obviously restricts as an action on ordinary categories. And the SO03 fixed points of it is equivalent with ribbon categories. Over C. So yeah, anyway, thanks to David for pointing out that a paper we had out there was close to establishing this. I think this is folklore, and it might even appear in some of your work or some work that's out there, but we couldn't find it. And I don't, yeah, so this is just for restricting the action to 1-1 categories. Just want to achieve that. And a consequence of this, just formally, and what I'm discussing here is on the archive, is an action of base loops of O of n on every one of these, as well as an action of base loops RP n minus 1 on the moduli space of objects of it. So these actions follow from this one. And again, we're thinking n is equal to 3, and base loops on RP2, pi 0 of it is not 2z, and pi 1 of it is z. And so this action is kind of familiar. This is abstracting, taking duals and abstracting the ribbon element. Like conjugation of the ribbon element. Oh, wait. These are 5-0-minute talks, right?
Yeah, but you were interrupted a lot, so.
Oh, well, that's generous. I'll just mention as a remark here, and that I conjecture, but I think this is hard, maybe in the way that you have in mind, that if you have a ribbon category, so an SO3 fixed point, then this is independent of framing. Of M's framing only depends on the orientation. If R SO3 fixed. I mean, this kind of statement generally is the type of statement to be expected, but following the construction of this is not obvious at all. And they noted that such a statement would be excellent to be able to interpret the excision statement as you'd like to, so that middle term is indeed alpha factorization homology. So
are you implicitly also saying that you don't have a descent statement for the tangle? You don't have that with the structure, or
excision is valid. It's just that that intermediate term is not as simple as simply the what you'd like it to be, the alpha factorization homology category.
But I mean, for the tangle hypothesis, right? Is that do you have the version with tangential structure? That you have version with-
Oh, I see. Oh,
and fixed points.
Oh, I see.
The thing you have.
that's yeah. So this is like the framed tangle hypothesis, and one would expect the the oriented version of the tangle hypothesis to follow where you up here you see the SO and fixed points, and that's another statement that does not just readily follow. I mean I expect that to be true, but I don't see how to show it. That's equivalent to saying that so this has an action of O of n, and that the O of n quotient or SON quotient is the oriented version. It's very believable, but quotients and colimits of infinity one categories are really complicated.
Just can you clarify what exact version of the frame, or what type of framings?
Yeah, thanks. So what this means is, one morphism in here. So a one morphism here is, it's a Rn minus one cross an interval. So it's a one-dimensional tangle in there. And a one-dimensional tangle is equipped with a Gauss map to RP n minus one of Gauss map. And it's a null homotopy of it. That's what I mean. It's the strongest possible version of a framing. Yes. Yeah.
But it's like very different than just like a framed tangle and like.
Right. It's explicitly it's the data of an orientation on the one-dimensional manifold, a realization of the normal bundle, but then more, and an identification of the resulting framing of the tangent bundle of the ambient space restricted to W with the standard framing. So I definitely should wrap up. So my plan was to indicate how the construction goes, and I'm happy to have that conversation with you, anybody later. I think what I'll say is that I mentioned this earlier, that these statements, in particular this one, is actually is used in an integral way to implement this construction. And the proof of this tangle hypothesis, this is a paper on the archive presently. We repeatedly use what I'll call hypercover argument. And that's just such an awesome tool that so like in proving the tangle hypothesis at several key junctures, we compute a colimit in infinity categories. And that's a really hard thing to do if you've ever thought about it. And the way that we do it is we have abstract formulas for what these colimits are. And then we match those formulas with open covers of moduli spaces of tangles. And we wrote this paper, and then shortly later, I saw that Jan Steinerbrunner and Schall Becker have a paper where they kind of have a general type of result for colimits and infinity categories. And it's an awesome paper because there's the formulas that we are kind of like wrangling with in very abstract terms, but at least it's like systematized enough that now in retrospect, it makes it easy to just take their formulas and try to match it with open covers. Anyway, so, well, thanks a lot for your attention. I look forward to more discussions.